Welcome to this class 12th, Unit 5, Electromagnetic Waves, Chapter 8, Electromagnetic Waves. And topic for today's discussions are Maxwell equations, displacement current, types of currents, electromagnetic waves, property of electromagnetic waves, HERTZ experiment, and electromagnetic spectrum. Maxwell rearranged four equations which are used in EM wave. Number 1, first equation he gives Gauss law of electricity. This is phi equal to EDS equal to Q upon epsilon naught. Second, he chooses from Gauss law of magnetism, that is BDS equal to 0 because magnetic flux cannot be started or not terminated. Actually, EM wave from comes from electric and magnetic, so he chooses first from electric Gauss theorem, second from uh, Gauss theorem from magnetism. Third, he took from Faraday law. Third equation, that is a Faraday law. This is EDL is equal to minus d phi upon dt. But in this chapter, we use both type of flux. So phi b is called magnetic flux. Phi e will be denoted for electric flux. And the fourth one in this ampere and circuital in place of ampere, Maxwell gave contribution and reform this equation. This is called Ampere-Maxwell law. This is BDL equal to mu naught IC plus epsilon naught d phi E upon dt. This term epsilon naught d phi E upon dt, he gives that as displacement. So new terms come here. Displacement current. What displacement current? Current produced due to change in electric flux is called displacement current. From fourth equation of Maxwell, that is clearly says that BDL equal to mu naught I, but here the I is a categorized in IC plus ID. So here ID is a new term, that is epsilon naught d phi upon dt, that is called displacement current. So here we have to remember that the change in electric flux is called displacement current, or ID is equal to epsilon naught d phi upon dt. But here is the electric flux, so we give us phi e here. How we can relate this displacement current, where it come? So we can take an example of capacitor. Capacitor can be charged by DC current. So one terminal will be connected by positive and second terminal will be connected by negative. This is the case when we are charging the capacitor. Capacitor is going to charge, it means current flow from our terminals, both terminals. That is called current passes through the conductor. So it is called conduction current. But what happens between the plates of capacitor? Plates of capacitor are the insulators where current cannot pass, but in series current remains same. So which current is can be identified between the plates of capacitors? Here, between the plates of capacitor, charge or electric flux is changing. So the changing electric flux can be categorized as displacement current, or we know that in series current remains same, so it means conduction current may be equal to displacement current. So how can we prove? ID equal to epsilon naught d phi E upon dt, but phi E from famous Gauss theorem, phi E equal to Q upon epsilon naught, so ID is equal to epsilon naught d upon dt. Q upon epsilon naught goes cancel, and dq upon dt is the current due to flow of charge. So it can be categorized as conduction current. Therefore, ID is equal to IC. Simple derivation. Now, on the basis of flow or the change, we can categorize types of current in four ways. First, conduction current. It is a current which we can actually know, that is a current. Rate of flow of electron, rate of flow of charge. So current carried by a conductor due to flow of charge is called conduction current. This is the famous concept. Second one we think about in the induction, induced current. So current carried due to change in magnetic flux. Here we have to identify the word magnetic. When the flux change, current induced. Which flux change? Magnetic flux change. So the current carried due to change in magnetic flux is called induced current. Now, third one that we heard now, displacement current. The current carried due to change in electric flux. When flux, which flux? Electric flux will change, then the current is called displacement current. One more current we will discuss in the next book this year only, that is photoelectric current. The current carried by the emission of photoelectrons, electrons which can coming out from the surface of metallic surfaces, which electron goes jump from the surface, metallic surface, actually alkaline metallic surface, which have very small threshold frequency. We will discuss in second book in a detail. The current carried by the emission of photoelectron from alkaline metal on incidence of light above the certain frequency. This certain frequency is called threshold frequency, and this current is called photoelectric current. And if any two of current or any of the four current are connected in series or passes in series, so in series current remains same. So we now in this topic we prove conduction current is equal to displacement current, and in the next book we will discuss the conduction current is also equal to the photoelectric current. Now our second topic is electromagnetic wave. This is the name of this topic in unit. What is electromagnetic? EM wave. So electromagnetic wave is a wave in which electric and magnetic field are perpendicular to each other, and due to oscillation of these two fields, electric field and magnetic field oscillating perpendicular to each other, suppose one is in x-axis, second is in y-axis, then perpendicular to both, third axis, that is z-axis, a certain type of energy will propagate. This energy is called electromagnetic wave. So we can show with the help of diagram also. It is a 3D diagram. There is a two component, electric and magnetic component, and perpendicular to both in the third axis, the EM wave will produce. Now we will discuss the property of EM wave. First, variation in both electric and magnetic field occurs simultaneously. It means both will goes in the same phase, but in different dimensions. One may be in x-axis, maybe, and other may be in y-axis. So the maximum minima in the same phase and the same time. This is the first condition. There must be the phase difference is zero. The direction of electric and magnetic field are mutually perpendicular as well as the direction of propagation of waves. It means we will get the wave in the third dimension. The electric and magnetic component, there are two components. One may be stronger, one may be weaker. So by getting the relation between them, E is C times stronger than B. Therefore, we get the speed of light C is equal to E upon B. It means which component is stronger? So electric component is 3 into 10 to the power 8 times stronger than the magnetic component. Definitely, we will get a more dangerous sign by the electric component, not from the magnetic component. Now, velocity of EM wave in the free space, we can just relate with the speed of light, that c is equal to 1 upon root mu naught epsilon naught, and which comes 3 into 10 to the power 8 meter per second, 3 lakh kilometer per second. The velocity of EM wave in the material, so then we will talk about the material. So mu naught will be replaced by mu, and epsilon naught is replaced by epsilon. That is the quantity of given material. Electromagnetic wave obey principle of superposition. They are the waves, and they are long transversal waves. They follow the principle of superposition as we discussed in class 11th. EM wave carry energy as they propagate in space. Actually, definitely they have a certain component of electric and magnetic, so they carry energy. They are energy waves. They have momentum. An electromagnetic wave can transfer energy as well as momentum to the object on the place of their path. We all again discussed. We have think about the cathode ray also. Uh, for discussion of optical effect, EM wave more significant given electric component. Therefore, electric field is light vector. Which component is more stronger? That is the electric field. Electromagnetic wave do not require material or medium to travel. We can just relate this property of EM wave with the property of light. So light is electromagnetic wave. So the property which can coincidence, which can be similar to the light, the property will be followed by electromagnetic waves. And oscillating charge which have non-zero acceleration can produce electromagnetic wave. There is a word that is non-zero acceleration. It means there must be acceleration. Now, there is a famous experiment by Hertz. Hertz is a unit of wave frequency. So, there is a large contribution of Hertz. That is an experiment known as Hertz experiment. He actually produced, he actually transmit, he actually show the demonstration of propagation, production, and detection of waves. He take two different electrode, like one is copper or zinc. They can take both of these, they will separate between them. He connect metallic rod and make a small gap by the two spherical balls between them. There is a small gap, like this. The gap can make a conditions for the sparking. Now he took a induction coil with the four electrode, and now he connect these electrode by one is positive and second is negative between the gap of the spheres, and the second he give the energy from the AC source. So on the certain frequency he get a spark between these two spherical balls with a certain geometry and certain distance between them, and a propagation of EM wave will transfer for a certain distance, and he can detect these waves with help of a loop and attached with again same types of spheres. So there he get a spark between the loop which is separated by these two electrodes. So this is the Hertz experiments. We can discuss an open metallic diameter. This is the approximate 0.7 and a small metallic gap. So Hertz first time show the representation or the transmission of a EM wave of the wavelength nearly 6 meter. And after 7 years, J.C. Bose, our Indian scientist, produced the wavelength and decreasing up to 25 mm to 5 mm. Now, the third topic is EM spectrum. What is electromagnetic waves and what is electromagnetic spectrum? So we know that the light is electromagnetic wave, and we know that light have 7 colors, but it is a one part of that wave. 7 colors is the EM wave. Now there is the invisible spectrum also: radio wave, microwave, infrared. There are 7 different components. So we arrange these components in order of wavelength or frequency. Number one, radio wave. This wavelength is few kilometer 2.3 meters. If wavelength is higher, then the frequency will be lesser, or wavelength will be lesser, the frequency will be higher. So we are going to the descending order of wavelength and ascending order of frequency. So radio has the highest wavelength. It may be a few kilometer also, from zero point 0.3 meter. Frequency will be 10 to the power 9 hertz range. It can be produced by oscillating electric circuit, as we discussed earlier in the Hertz experiment. What the use of radio wave? It can be used for the transmission, for communication, for entertainment, for broadcasting, for communication. So radio wave and TV. Now, second one is the second in order of descending order, that is microwave. Its wavelength is 0.3 meter to 10 to the power minus 3 meter. Frequency range is 10 to the power 9 hertz to 3 to 10 to the power 11 hertz. We can find the frequency by the formula of V equal to nu lambda, C equal to nu lambda. So nu equal to C upon lambda, and by putting the value of C equal to 3 into 10 to the power 8. So it can be produced by oscillating electric circuit, same as above. It can be used in radar. The full form of radar is radio detection and ranging, but it uses microwave analysis of fine detection of atomic and molecular structure, and also in microwave oven. What is the concept of microwave oven? Microwave oven produces the microwaves. What device produced microwave? That is the klystron valve, magnetron valve, or contact diode or gun diode. These types of instrument use microwave. These are attached in microwave oven. They produce microwave, and the frequency or the wavelength of microwave is in order of food particle. So they produce the condition of resonance, and the food particle get energy in form of heat. Now, third one is infrared wave. This is also called heat waves because the component which is responsible for heat in EM wave, that is infrared, the range of infrared rays is 10 to the minus 3 meter to 7.8 into the minus 7 meter. The frequency range for the infrared is 3 into the 11 hertz to 4 into the 14 hertz. What is the source? By getting the heat wave, there is a molecular and hot bodies, vibrations between the particles that can be exhaust energy in form of heat. What is the use of this heat in our industry? Where we have to dehydrate the chips, fishery industries, we have to dehydrate the fish and meat materials, medicines, astronomy, night vision device, a greenhouse, revealing the source secret within the ancient walls. Or we can also can fog photography because we also have a certain type of lamp in our car that is called fog lamp because they produce infrared and infrared melt the fog so the vision goes longer. Our next component of EM wave is light, which is visible spectrum waveguide. It's a range of wavelength is 7,800 angstrom to 3,800 angstrom. A range of frequencies 4 into 10 14 hertz to 8 into 10 14 hertz. Very small part of that. Whole spectrum, light visible is a very small portion. As is the waveguide. What is the source? Atoms and molecules when the electrons are excited. Then we get the certain type of frequency and wavelength. Uses to see optical instruments, vision, photography. Next one is UV rays, ultraviolet rays. This is a component which gives us certain types of harms and maximum types of uses. It is a small enemy which can harm us a little bit. It can, but we can use in a multiple ways. Uh, we can also get protected from UV rays from ozone layer. Ozone protect us from UV rays, but certain chemical harms ozone layer that are CFC, chlorofluorocarbon. So there is a certain type of cavity inbuilt between our ozone layer above the California. It's called ozone hole. So what is the UV rays? So UV rays, the wavelength is 3.8 10 to the minus 7 into 16 to 10 to the minus 10 meter. What is the frequency range for that? That is the 8 into 10 to the 40 hertz to 3 into 10 to the 17 hertz. How they can produce atoms and molecules in electrical discharge and sun is obviously the ultimate source of energy. Uses now there are the versatile uses, medical applications, sterilization because it can kill small types of bacteria, insects. So it can sterilize the surgical instruments, killing bacteria, germs in foodstuffs. Actually, it can kill. So it can also use in UV used in your water purifier. So UV detection of invisible writing. So it can be also used in forensics for forged documents, currency check, fingerprint, multiple use, LASIK. LASIK is the surgery of eye in this UV rays used. Next one is X-ray. X-ray is we think that is a medical terms, but it's a waves. So X-ray range is 10 to the minus 9 meter to 6 into 10 to the minus 12 meter of wavelength. A range of frequency is 3 to the 17 hertz to 5 into 10 to the 19 hertz. We know that when the frequency get increased according to E equal to S nu, its energy will also increase. So when we increase the frequency, its dangerous effect will also increase. So we get very small types of harms from UV rays, but we should cautious from X-ray and very cautious from gamma rays. So X-ray can harm us definitely, but they use because due to medical terminology for a few nanoseconds they can give us X-ray photography, treatment of cancers that is called chemotherapy, radiotherapy, skin diseases, tumors, locating cracks that is called X-ray, and flow in finished material metallic object. In Bhopal, we have a BHEL, Bharat Heavy Electrical Limited. In that factory, we built a very heavy machinery. And if there is a certain bubble occur between the molten iron, how we can detect or how we can find the strength of that bar, so that can be calculated by or measured by X-ray. Or X-ray can also use, we think about the security check in the airport or very sensitive zones. So without opening the bags, we can check the security of the material placed inside the bags. Or it can also used to check the crystal structure, like the diamond, the purity of diamond, cracks in diamonds also, cracks in gems also. Last one is gamma rays. It is a very dangerous ray, and this is a component only in the EM wave, which is also available in radioactive decay. This is the component which is also available in radioactive decay, alpha, beta, and gamma rays. These are the energy waves, truly energy waves. They overlapping the upper limit of X-ray and up to goes up to 10 to minus 14 meter, up to 1 Fermi. Range of frequencies 3 to power 18 hertz, 3 to power 22 hertz. They can emitted by radioactive substances, information or uses. They are used in radioactivity, artificial element, nuclear fission, nuclear fusion, formation of cobalt, artificial nickel, or we can also research purpose, or we can get a element that is called artificial elements. This is a certain type of pictorial diagram that we can know that when we frequency increase, we get from radio wave to gamma waves. In the very small portion, we get visible rays, and we know that the red color have highest wavelength in visible region, and lowest wavelength violet in visible region. But beyond this, we have a broad spectrum of invisible region. This is another pictorial graph by the showing what are the uses, what the frequency range, and what are the temperature of the body emitting from that wavelength. If we want the certain type of wavelength, a material or substance must have a particular range of temperature. Now another pictorial graph we can get the uses like the radio waves. What are the uses of radio waves? What are the use of microwaves? What are the use of infrared? What are the use of visible light? What are the use of UV? We also get UV goggles. Uh, Whenever we are seeing the welding machines, they are using certain type of spectacles to avoid from the UV rays because that spark is creating UV rays also, X-rays and gamma rays. This is the symbol of hazard. This is a symbol of hazard. Apart from this, we can also discuss in all the spectrum component, one thing is similar. This is speed. Speed of all the waves or the component is same. Speed of all the component is same. In vacuum, that is 3 into 10 to the power 8 meter per second. One more thing we can discuss is when one medium to another, that is called refraction, then the frequency will remain same. Thank you.